Hello and welcome to the fifth and final video related to piston and cylinder example problems. So we've gone through something that's pretty simple, something that's pretty complex, and now let's look at the final example I want to share with you. So again, be a piston and cylinder undergoing a process, and we're going to use only SI units for this problem. Okay, so I'll read it as you read along. And I see there's only a part A associated with this problem. It says, a gas is contained in a vertical cylinder fitted with a piston on the top and closed on the bottom, just like all the previous four. Okay. The initial volume of the gas is 0.25 cubic meters. The piston is locked in place so it cannot move relative to the cylinder. The piston has a mass of 25 kilograms and a diameter of 18 centimeters. Atmospheric air surrounds the piston and cylinder, and the pressure of the surroundings is 1 atmosphere. On Earth, the acceleration due to gravity is 9.8 meters per second squared. The gas is heated until the pressure triples. Just one question: determine the work done by the gas during this process. Okay. Well, let's see. What should we do? Based on what we did for the first four. Start with a sketch, maybe? I think that's a fine idea. And I guess before we start with a sketch, let's, as we read the problem, let's here look for key words. Cylinder fitted with piston. You're starting to get familiar with my, I hope you're developing a habit of writing down when you draw your sketch, write down closed system for this type of process. At least you recognize it's a closed system. Okay. Piston is locked in place so it can't move relative to the cylinder. It says no piston motion during the process. There's a pin put in into the side of the cylinder and locks the piston in place. The piston has a mass of 25, diameter of 18 centimeters, et cetera, et cetera. I'd say lots of information provided here. And a process description. It says the gas is heated until the pressure triples. Okay, all right. Determine the work. Well, and so when you see work done, you got closed system, what's the work? You're basically thinking use integral PDV to determine the work out. Okay, next, draw the sketch. So I said, what's the first thing we do? Well, as we read the problem, we look for those key words, and then we draw that sketch. Okay, and so here's my sketch of my equipment setup, and I've drawn a pin in the piston, locking the piston in place relative to the cylinder. And here's my control surface. I've got a fixed mass in here, and I've got Q in, and I'm showing work out, but this piston's not moving. Okay. So for this problem, you need to apply a little common sense 101 here. The piston's locked in place, so the volume of the gas doesn't change. And so in your mind, what I want you to visualize is that for this situation where the piston is locked, that's equivalent to basically a rigid vessel, a plain old rigid vessel, okay? And so there are times where you will have homework problems where the words say rigid vessel. It won't say piston with a locked in place. You're not going to get that out of the textbook, but there will be lots of problems where it says a rigid vessel. So that's your key to say fixed volume. Volume is constant. Volume is constant for a rigid vessel. Makes sense, right? Okay. Let's do the homework problem. Determine the work done. Well, this is where a PV diagram will really pay off for you. So, okay, you got the part about work is integral PDV. All right, you got that part. But let's draw a pressure volume diagram of this rigid vessel where heat is being added. We're adding heat. We got a flame underneath this rigid vessel. we're adding heat to the gas inside here. The volume doesn't change. So the process path is a vertical line. The volume is constant. The volume doesn't change, but the pressure triples. Okay. What's the area under the curve for this process? The area under the curve using your eyes is 0. That's common sense 101. So you don't even have to do the fancy math to determine that the work is 0. Now, if you do want to do fancy math, let's look at the fancy math. Okay. Recognize that if volume doesn't change, that means that dV equals 0. That's the mathematical way to say the volume doesn't change. dV equals 0. The incremental change in volume is 0. No change in volume. Okay. So when you do the integral and dV is 0, the integral result is 0. So the math agrees with common sense 101. And if this were a homework problem and I had to turn it in for credit, what I would do would be I would write out in words and circle it. There is no work done by the closed system during this process. So that's the answer. That's the answer to this problem. No work done, 0. Okay, so what's the recap? Look for keywords in the problem. Start with a sketch. Sometimes in problems, particularly in quizzes and tests, and particularly if you have me as an instructor, you have to watch out for non-needed information within the words of the problem. So there's nothing that says an instructor has to give you exactly the numbers needed to solve the problem and nothing more. An instructor is certainly free, and other engineers are free to give plenty of it, more than enough information, some of which is not needed. And isn't that a lot like the real world, where you have a real world problem? You've got everything available around you, and you can look at the time of day, and gosh, you can think about what you had for lunch, and all of this information available to you, but it might not help you solve the problem. And so you got to watch out for non-needed information as you're training yourself to be a good practicing engineer. So, and then also for this particular problem, we saw that we can use thermodynamic fundamentals to explain what you see simply by using common sense 101. And so this one was really, wasn't this an easy problem? Work equals 0. And so it's a good example of where you don't want to make things harder on yourself than you have to. And so that completes, that's the 5th module set of example problems associated with piston and cylinders. I hope you've gotten something out of the whole package. So we started off simple, a constant pressure piston and cylinder process, constant pressure process. You're going to be doing a lot of those, right? The second one, we made it more complex by adding a compression spring so that the pressure curve, the pressure path was a linear path. Then we did one where the path was defined, PV equals constant. Now you're going to be, when we introduce ideal gases, you're going to be dealing with that process path a lot. So that's a special type of path for ideal gases. Won't give you more details now, but you're going to quickly learn about it, okay? And then in the 4th one, we had a difficult path, a polytropic process path, where PV to the N equals constant, where N is some number bigger than 1, like 1.3, 1.4, 1.5. And it does turn out that for ideal gases, that's another special type of process that in this class you're going to be using a lot. So the more comfortable you can get with doing that integration on your own without using formulas is going to pay off for you in terms of your performance on quizzes and tests in this class. So good luck with the rest of the class. I hope that these videos will have helped you Would appreciate your getting back with me, and let me know if it helped, didn't help. What would you like to see differently? Of course, I'm fully supportive of the course content. It's not like I can't decrease the course content or make the content easier. The course content is difficult, so I do want to help you get better at performing well with all of this difficult course content. So see you again soon.